Y'all? Welcome back to another ANSYS YouTube tutorial video. Today, we're doing... Wait, I forgot what we're doing. Hold up. We're doing fluent flow over a semi-cylinder. Let's get right into it. So, the first thing, as with any project on Fluent, is to drag out a fluent from this side. And since this is a 2D project that the geometry can be done relatively quickly, we're just going to do the geometry in ANSYS. So we come back here. We're going to do new design modeler. And this is going to take 3 years to load. There we go. We're going to start sketching on the XY plane. So the first thing we're just going to want to do is just make the general shape. We're going to make a bunch of lines. And then we're going to go to circle. Why is that not snapping? Alright, I just have to assume that that's snapped properly. We're going to dimension everything. This diameter has to be 1 millimeter. Diameter 1 millimeter. Gonna make this like 10. Gonna make the height like 4. That is not the height. This is 4. We'll make this 4 as well. We'll make this 9 actually. And this is what we want for the half body. However, I believe I have to cut out the bottom half of the circle. Back after the troubleshooting, the best way to represent the cylinder, the partial cylinder, would actually be to do an arc. So we take the center here. And as we can see, we have all the right constraints. So that is our semi-cylinder. Then if we go to concepts and surface from sketches, then we can click this, 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 this. Click apply. And then click generate. And we are just going to suppress that because I don't care about this. And for some reason, it does not let me delete it, which is pretty cool. If I try to cut it. Okay, there we go. Never mind. I'm just an idiot. Nice. Okay. So we now have our model. It is, Let me just double check that that is a meter. Okay, the radius is zero point 0.5, so that is checks out perfectly. It is 4 meters long on both sides with the height in the V. And it's not in the shape of a wind tunnel, so we don't need to worry about that. So this suffices for the simulation.
Now to move on to the meshing part. Um, since I forgot to save the original clip that I used to record all my meshing stuff, the mesh is already done. And I just realized this halfway into the gathering results process. So yeah, basically all I really did was I came into the mesh settings and played around with the element size until I got to 1.5 e to the negative 2 meters. What this gave me is 320,000 total elements, which is under our limit as a trial student, and it looks to be fairly precise, so I'm going with this. Additionally, we made name selections by coming over to selection, create, name, and I named each wall specifically what they should be. And just to go over how to adjust the element size, you click on mesh and then come here to element size and click P and it locks it in. So yeah, just a small note in between meshing and going to the setup. You should make all of your walls name sections. I originally forgot to do this when I was doing the mesh in the first place, but this is very important so that way you can set certain properties for your specific lines and sections, which is apparent when we go into here. As we can see, now we have our name section. So now, like if I want to adjust the velocity in, we go to the inlet, come over here to look at what we need to do, which we're doing part 2. So our free stream velocity is 30 meters per second. So then we come back here and we go 30 meters per second. And we just apply that. And then just to check the density, because it did also say that, density should be 1.2. Nice. And then everything else looks good. And then we just need to worry about the model we're using. Steady, viscous, turbulent. And we are using K omega, but we'd want to use K epsilon. Just leave all this other stuff defaults. Click OK. And we should be good to start generating the model. So we go to initialization. And then we initialize. You go to calculation. Set the number of iterations up to something like 50. Say 100. And then we calculate. And there we go. It's starting to calculate. Now this could take a while. So we're going to cut to when it's done. So in order to do the first part, we need to get the contours of velocity, pressures, and path lines. or streamlines. So as you can see, here's the velocity contour already. Basically, you just come over here to contours, and you just velocity, save and display, and then for pressures, change it to pressure. This is static pressure. This is dynamic pressure, and this is not absolute total pressure. As you can see, total pressure remains relatively constant, which should be, except at the big vorticity here, there's a significant drop in total pressure. And then in order to look at the streamlines, what we're going to do is we're going to come over here. We're going to select interior surface body, but we're going to lower the step count significantly. So that way we can actually have it display instead of taking 12 years to download like previously. So let's wait for it to load though. And there we go. Now this, just looking at it like this doesn't really make any sense. So you have to zoom in to really see the lines. Obviously, each of these represents a sort of streamline. So let's say we go in here. We can see that the gas sort of does this upward motion, and there's a vorticity created here. And it generally falls pattern. And then if we go over to here, we can see that the flow separates at this point here. And there's it's actually a pretty big vorticity here from what we can see. Gas goes around like this, and then that causes the flow down here to flow up like this, which causes the separation here. And this vorticity also pulls in from significantly far away. Like it's pulling in from here, which is probably like almost a meter, half a meter, honestly. So the vorticity is pretty big. It has a pretty big influence on the flow. So that is part A. Yeah. On to part B. Part B, we need to get the velocity and the pressure coefficients on the surface of the half cylinder. So we go to XY. Let's say we're going to do the pressure coefficients first. We're going to want the X function to be the direction vector and the surface to be the half cylinder. Save and plot that. We get this graph. Obviously, it's going to start at 4 and end at 5 because that's the respective X direction. So we get this graph. And then let's say we want to look at velocity. We get velocity and it is near 0. Not quite though. That could actually theoretically be 0. Basically, what causes this is obviously it's on the surface of the half cylinder, so viscous effects are going to take into place, and it's obviously going to no slip condition. Velocity is going to be 0. So, yeah, that's really what's causing that. And there is our part B, our velocity and coefficient of pressure mapping along the surface of the half cylinder. All right, I figured it out. It is very important that your reference values match that of your actual setup. There we go. So before I redid this, I had velocity on 1, and that gave me a coefficient of pressure of 300, which is obviously extremely unrealistic. Therefore, set it to 30, and now I get 0.42. And just to see, we are going to redo it in this direction on the half cylinder. And we get a much smaller coefficient of drag of 0.01. So yeah, we experience a lot of lift, not so much drag, and yeah, that's that. Thank you guys for watching the tutorial video. I hope this was helpful somehow, some way. And yeah,